In everyday life, salt is the stuff that you season your food with, that we pour onto the ground to prevent icy roads, that exists in our oceans, and so much more. Now, this is usually just sodium chloride, NaCl, or table salt, but in chemistry, a salt is a compound that is really any mix of ions. Sodium chloride, as the name suggests, is made up of sodium cations and chlorine anions. And just as a reminder, a cation is positively charged. Think of cats with paws. And an anion is negatively charged. Typically, elements in group 7, like chlorine, fluorine, etc., will have a -1 charge. Elements in group 1, like sodium, lithium, etc., will have a +1 charge. And elements in group 2, such as calcium, magnesium, and others, will have a +2 charge. If you're ever uncertain about the charge of other ions, just remember that the total charge of a molecule must be equal to the sum of its parts. So for example, strontium sulfite or SrSO3 will be made up of Sr2 plus cations, which I know because strontium is a group 2 element. And as such, the anion sulfite must have a -2 charge to balance out with the cation. When a salt is dissolved into water, it separates into its cationic and anionic counterparts, which is a process that we call hydrolysis. You've probably actually seen a lot of these common ions in your acid-base chemistry experience already, like how Cl- is the conjugate base to the strong acid HCl. Since HCl is a strong acid, that makes Cl- an extremely weak base. So weak, in fact, that it sort of just does nothing in water. We call these do-nothing ions spectator ions, and they're just the non-H plus or OH minus parts of strong acids and bases. So looking at our list of strong acids and strong bases, then that means that all of these non-H plus and non-OH minus parts are spectators. And these spectators won't mess around with water like a normal acid or base would, so we can think of these ions as neutral, not by charge, but by pH. So any salt of a strong acid and a strong base, something like sodium chloride or calcium iodide, will result in a completely neutral solution. But how about all of those non-spectator ions? These are ions that will actually interact with water and therefore will affect the pH. These are going to be ions that belong to weak acids and weak bases. You know, like acetate comes from acetic acid, or ammonium from ammonia. They're the conjugate base to a weak acid, or the conjugate acid to a weak base. If I have a salt of a weak acid and a strong base, maybe something like potassium acetate, the salt as a whole is going to have more base character, and as such results in a basic solution. Think of the acid and base as competing forces. Since the acid side, acetate, is weak, and the base side, potassium, is strong, the basicity is going to overpower that acidity. Likewise, a salt of a strong acid and weak base will be more acidic in nature, producing an acidic solution. The final scenario, which we haven't looked at yet, is a salt of a weak acid and a weak base. This situation is a little trickier, but we'll use the same logic in comparing the acid and base as competing forces. As an example, let's look at a solution of ammonium formate, or NH4HCOO. So ammonium is the conjugate acid to the weak base ammonia, which has a Kb of 1.8 times 10 to the minus 5. And formate is the conjugate base to the weak acid formic acid, with a Ka of 1.8 times 10 to the minus 4. So just comparing the weak base ammonia and the weak acid formic acid, we can see that formic acid has a larger Ka than ammonia's Kb. That translates to formic acid being stronger than ammonia, and hence the salt is more acidic and character. So this solution is mildly acidic. To summarize, a salt is just a mix of positive cations and negative anions. A salt of a strong acid and a strong base will result in a neutral pH. A salt of a strong acid and a weak base will be acidic. A salt of a weak acid and a strong base will be basic. And a salt of a weak acid and a weak base really depends on the relative strength of those halves.